For this, I would like to present some test benches that you can use in LT-SPICE to test. It says place your transistor in it, um, adjust the parameters, and see if you can meet the specifications. And we have seen several solutions in the homework. So we are also presenting several solutions that are more or less compatible with what we have seen in the homework. So the first one is basically what we have discussed during the lectures. We have a kind of indirect feedback biasing because in one circuit we use the MOSFET and we have a feedback to generate VGS, and this VGS is with a gain of unity copied to the lower circuit in this controlled voltage source, so that the lower circuit is exactly biased, but now we can also drive it with a voltage. So this is the driving voltage at the input. We have the load, and RL can be, well, whatever you want, 25 ohm, 50 ohm, 100 ohm, depends on the situation we want to study, and that has been discussed in the drive requirements. So this is the indirect feedback biasing solution. There's also a direct feedback biasing solution, and that is, I think I presented this in one of the lectures as a result of a question. So then we have a feedback here for the biasing, which is DC, but a capacitor and a resistor, let's say a low pass filter, that uh, kills all the feedback for frequency range of interest, which means that for the frequency range of interest, we just have the correct operating point, and the control source is not changing its value because there's simply uh, no signal at the input. Of course, you cannot put a nuller there. If you put a nuller there, then whatever the voltage is, it will nullify the difference. So then for all frequencies, you have no signal left. So this is a solution that you can also use. And we have seen other means, because here we are really making a drive voltage and we can put any shape of the drive voltage there. But basically what we are interested is just the design of the FET. We just want to know what is IDS and VDS and what should be W and L of the FET. So that's the only question to be answered. So a simple DC sweep with a biased FET would also be okay. And that is this I call it swept input. We just have a VDS we connect with the load resistance, and we apply IDS, and we sweep with the voltage. And of course, if the voltage is 0, then all IDS is flowing through RL. And if the voltage is 1.8 volt, then hopefully all the VDS is generating a current through our RL, which flows through the FET together with IDS. So what we need to do is we need to make VDS larger than the peak voltage drive requirement. That is what we have seen in the biasing, in the basic treatment of the CS stage. IDS should be larger than the peak current drive requirements. L should be the smallest value. Why? Because we are interested in showstoppers. If L is the smallest value, and we need more than the power supply voltage to drive it to get the desired output range, then it's not possible. If you start with a longer L, you can also always make it shorter. So you start with the shortest value of L, because we are dealing here with drive capability, not with frequency characteristics, not with FT, not with distortion. This is all not what of interest now. We are just designing a FET that has sufficiently large drive capability. This is also distortion, but it's called clipping. So that's what we're doing. And W should be large enough. So you take the smallest L, you make W large enough to ensure sufficiently large drive capability. Many of you did this in one or another way, did this okay.